Okay, so the last topic is friction. Oh yeah, good question. The final is um, Friday. I can tell you. I'm gonna get it right now. Okay, don't read my emails. Don't read my emails from the Beanie Baby Appreciation Society. um, okay, so Friday of next week at 11, and it's in a different room, which is a nuisance. Oh, is this actually this one might be in the same room? 2030, that's this, right? Yeah. Oh, okay.
It's very nice.
Yeah. So the final is next Friday.
The 19th, right?
Yep. 11 to 1 in C 2030. And the topics, everything before friction. So no friction. Okay. Any questions about the final?
We're going to learn friction today.
Yeah.
Okay.
Yeah, so we'll talk about it today and Friday. Okay, so the last topic is friction. And there are three sort of subcategories of friction that we're going to deal with. The first one is square threaded screws. The second one is belt friction. And the third one is bearing friction. Um, and there are two types of bearing friction that we'll talk about. Journal bearings and thrust bearings. You know, we'll see how much of all of this we'll get through. Maybe not all of it, but like I said, this is a topic that is not going to come up for most of you in future classes at all. It is kind of cool though. And one thing to keep in mind about this, so whenever you're talking about friction in any class, you know, it's usually like a topic at the end of most classes in some way. Ask yourself, would I most likely be dealing with a dry type friction, or would I be dealing with a viscous friction of something that's like bathed in oil, for example? This is all of this theory here is related to dry friction. And so any kind of lubricant that you use that depends on viscosity is viscous friction, viscous damping. That's a different kind of math that you have to deal with. So this would be like for stuff if you're using some kind of what do you use the like in the Pinewood Derby or whatever, you spray that yeah, like right. This would be like graphite lubricant kind of stuff, something that's not depending on liquid qualities for the damping. Okay.
So that's like is viscous but turns dry like glue, like with glue. Would that provide some form of
Yeah, I mean, I guess it depends on how it's acting as the motion is going on, and I don't have an answer for that in very many specific cases. They're like, for example, for bike lubricants, like a lot of times you use like sort of a waxy coating, but that wax still behaves like a viscous lubricant because when you start applying forces and stuff, it forces liquid out of the structure. So, just be aware that what we're talking about here does not work well for motions between things that are lubricated by oils. Okay, so square threaded screws, that's the first one. And so we're talking about something like this. So these are my guidelines. You don't have to draw this yet. You don't really have to ever draw it. This is America. Why does it? Okay, so there's a square threaded screw. Okay. Yes.
the edges are square?
Yes. So let me draw the alternative would be a screw like this. Okay. So not this. The one on the right, that's like if you go buy a box of screws at the hardware store, the profile looks like this, the threads look like that. This is a lot easier to mill, and
It's a lot easier to screw as well. If you wouldn't have to have pre-threaded things. It would be much.
well, yeah. So like wood screws are like this, but so keep this distinction in mind. The calculations that we're going to do, the derivation that we're going to use depends on the shape of these threads. And what we're going to see as we go through the derivation is there is a reason, like why would you go through the extra energy to make bolts and screws with a profile like this? They can support a lot more force. And so in cases where you have a bolt or a screw that has to support a lot of weight, you'll go through the process of doing it like this. And I'll talk about why that is. So this can handle bigger forces, but it's more expensive. For example, the threads on like a car jack are square threaded like this. Okay, so the physics of square threaded screws. Depends on, so maybe when you took physics, you wondered when this was ever going to come up in your everyday life. But it depends on the physics of sliding on inclines. So for example, let's just go back and do a quick refresher. So imagine you have a box that's on an incline. Let's say that this is, what does that look like, 10 degrees? And let's say that this has a mass of 20 kilograms. And let's say that there's a force pushing it up that's horizontal of 10 newtons. And let's say that the coefficient of static friction is 0.1. Okay. If the box starts at rest, will it start to slide up the incline? Okay. Well, do you remember how you went about this in Physics 1?
We used a rotation matrix?
Yeah. Did you use a rotation matrix?
No.
Oh, okay. But yes, you can use a rotation matrix, but you use the rotated coordinate system.
Yeah.
So okay, and you just did it by drawing out the triangles most likely, and came up with the.
My method was always just like to create a free-body diagram, create the point vectors, and then just take their components from the angle and then just use those.
Yeah. Well, let's do it. How do I want to do it? So let's draw a free body diagram first. We have a weight force down of 196.2. We have a normal force perpendicular. We have a 10 Newton force. And if we assume that this friction is strong enough to keep this from starting to slide down the ramp before you apply that force, then in order to keep this from moving up the ramp, we have to have a friction that opposes the direction of that slide. And so the friction is this way, and this would be the static friction times the normal. And what I'm going to do is I'm going to assume that this is in static equilibrium, and I'm going to assume that it's right at the limit of so I'm going to assume it's in static equilibrium. And how the hell am I going to do this? Okay, yes. No. Okay. So, right. I made this example a little funny. That's all. So we're going to see, let's think about it like this instead. Let's call this force Q. And then let's ask the question, at what Q will this start to slide up the incline?
Professor, is the Q force parallel to the horizontal, or is it?
It's horizontal, yeah. So at what value of Q will this start to slide up the incline?
It's from rest, right?
Yeah. And I'm going to use a coordinate system that's rotated like this. So we can use a rotation matrix here if we think. So a bunch of these things are easy to represent in the rotated coordinate system. A couple of them are easier to represent in a standard coordinate system. And so I'm going to use a rotation matrix to represent these two that are kind of more complicated in the rotated coordinate system. So let's think about a rotation matrix that takes us from something like this to something like this. That requires a 10-degree rotation. Is that clockwise or counterclockwise? It is one. Okay. So counter, right. So the rotation is going to be positive 10 degrees. And so my rotation matrix is going to be cosine of 10, sine of 10, negative sine of 10, cosine of 10, which is 0.985, 0.174, negative 0.174, 0.985. And now I'm going to use this to come up with in the red coordinate system, expressions for that Q force and that weight force. So we have 0.985, 0.174, negative 0.174, 0.985 times, let's do the weight force first. In the coordinate system on the right, on the left, that weight force would just be 0, negative 196.2. Right? Are you with me on that? And so I'll put in 0, negative 196.2. And then I'll do this matrix multiplication. And so we have negative 34.14 for the x component. And for the y component, negative 193.26. And then I'll do the same thing with that force Q. So 0.985, 0.174, negative 0.174, 0.985. In the original unrotated coordinate system, that Q vector is just Q0. So this comes out to be 0.985 Q, negative 0.174 Q. And now we have everything we need to fill out Newton's second law. If you remember when you did this in Physics 1, this was before you ever talked about rigid bodies, moments, anything like that. So all we're using here is Newton's second law. So Newton's second law says 0.985 Q, negative 0.174 Q, plus negative 34.14, negative 193.26. Plus 0n. Plus negative 0.1n 0. And since we're finding the exact value of Q where the friction force is a maximum before it starts to move, we're going to assume this is in static equilibrium. And so we have two equations for two variables. We have that, so I'll write it as n minus 0.174 Q is equal to 193.26, bless you. And then the second equation says negative 0.1 n plus 0.985 Q is equal to positive 34.14. And there's a few ways you could do this. I guess I'm going to just keep going with the way I have normally done it in this class. We'll write out the matrix. So here's n, q, and constant. Here's equations 1 and 2. For n, we have 1. For q, we have negative 0.174. For the constant, we have 193.26. Then for the second equation, n, we have negative 0.1. Q, we have 0.985. Constant, we have 34.14. Thanks. Is that what you were going to say too? Okay. So the surface area of contact doesn't come into the calculation. So we are going to think of a screw thread sliding on like a nut thread, let's say, as, so here is our screw. We're going to think of the entire thread of the screw as concentrated into one little spot like this. This would be a terrible way to make a screw. And it is sliding around a path like this. You with me on? So the red is like the thread of the nut. And as you turn this screw, that little box is just sliding its way up the ramp. Okay?
And we're unscrewing?
It doesn't matter which direction you're going. I mean, I guess the only way it's going to matter what direction you're going is whether you're going in a direction that fights gravity or whether you're going in the direction that gravity is sort of your helper.
I think ascending is a better direction because it's easier to screw up.
Well, okay, so this is going to be modeled by this. And we're going to have a cue doing this. Now, I guess one thing that's worth thinking about is we always have had a weight on the boxes that you've used in like Physics 1. So what does that weight represent? We don't really care about the weight of the screw. But really, that weight is going to represent some external force that's being applied here. And so we'll have a downward force, W, like this. A normal force, and depending on the direction of Q, you'll always have the friction force going in the opposite direction along the incline of what that force is applying. So this direction depends on the direction of the slide. There are two things we're going to do to modify this problem so that it makes sense for the kind of questions we're going to ask with screws. So two modifications. So the first one is, instead of being given an angle, like a ramp angle, we'll be given either a pitch or a lead. And these two things are related to each other. And that's just a manufacturing thing. I mean, it could easily have turned out that when we talked about threads, we talked about the angle that they rose. We just don't talk about it that way. And so this is just using the language of that, manufacturers have developed. And so here is the idea of pitch and lead. So for single threaded screws, which is the most common, if you think of, there's the thread, and imagine like an ant walking his way along this thread. You would see the ant here. And the next time you see him come around to your side of the screw, you would see him here. So that's what a single threaded screw is. So in that case, the pitch is this, and that's also the lead. So these are the same for single threaded screws. There are also such a thing for square threaded screws as double threaded screws. And so the way those work is here you see the ant walking up, but the next time you see, and he's going, climbing up this ramp, but the next time you're going to see him on your side of the screw, he's not going to be at this next one, he's going to be here. This is a double threaded screw. And the meaning of the pitch is how close these threads are to, adjacent threads are to each other. So pitch still means the same thing visually, but the lead has to do with where that single thread goes. So the lead in this case is twice as big as the pitch. So in this case, L is equal to 2P. In this case, L is equal to P. Yes?
The screw is embedded in material. Would there not be friction pushing on the top or on the bottom thread of the screw as well?
So that is the normal force.
But I mean, on the top, would there not be another force pushing back on the thread?
Oh, on the thread.
It's encased in material.
Right. Okay. So now I guess we're gonna just picture it with a little bit of like laxity. So you either imagine that there's a little amount of relief. So like if you push down, you hear a thunk. If you push up, you hear a thunk. So we're just gonna assume that it's on one side or the other.
Also, that same for the other side. Cause, if it will perfectly fit, the edge of the screw would also be rubbing up against the material.
Okay, how about this? Everybody just try to listen to what I'm saying and try to understand that, okay? I think it'll work really well that way. Okay, so what we want is the lead. If you have a single threaded screw, the lead is equal to the pitch. We want the lead. And if you you want to equate that angle to the, okay, so we're used to dealing with these boxes on inclines in terms of an angle, like this. In order to relate that angle to the lead for this screw, we're going to have to picture taking that thread and straightening it out, okay? And the lead is going to be this height. And then the horizontal leg is going to be the circumference which is 2 times pi times the radius of that screw. And you can think of that as like kind of like an average radius, like in the middle of the thread. Then that theta is going to be the inverse tangent of the lead over 2 pi r. So that's the first modification that we're going to do so that this block on the ramp makes sense as a screw problem. And then the second one we're going to do is that force Q that I've been giving is sort of a contrived thing. Like that would be like the equivalent of taking a little, like a toothpick, and turning this screw by pushing on a little notch in the thread. And you wouldn't do that. So we're going to replace that Q force with a couple that you would get by turning like a crank or a wrench or whatever. So instead of wanting an applied force Q, we want to find a couple that I'm going to call capital M moment. And so the relationship is that that moment is going to be equal to this imaginary Q times the moment arm of this Q, which is the radius of that screw. And so if you want to use that variable M, you can think of this force Q as just equal to M divided by the radius of the screw. Okay, so now we have the kind of problem that, yes? What? I'm sorry? Oh my gosh, I almost forgot the quiz again. Let's do the quiz on Friday. Okay, forgot the quiz again. Thank you.
Okay. And what happens if on Friday?
Then we'll just have 3 quizzes. But man, I'll remember it on Friday.
Okay.
I really thought I was going to remember it today.
This friction stuff is very interesting.
It's very interesting. it really catches your attention, sucks you in. Okay, forget it. We'll do an example.